All right, happy Monday, guys. Woo. Monday. All right, let's go ahead and get started. I can feel a buzz of excitement in the room today. I know it's not about OChem, but we'll use and feed off that energy. All right, so the other day we got started in whatever chapter number this is. We talked a bit about conjugated dynes. We're going to continue that discussion now. The stuff that we're going to discuss immediately is going to be leading into a larger discussion of a particular type of reaction that conjugated dynes can go over. But before we can get to that, we need to discuss sort of a new aspect of stereochemistry. Ooh, everybody loves stereochemistry. All right, I know, right? It's pretty cool. Anywho, let's go back and review a little alkene stereochemistry. All right, and this is all basic stuff. You know this. All right. As you've learned in the past, we can describe the relative positions of single bonds around double bonds. Right, like in this case, we have a double bond right there. And we can look at the relative positions of this single bond coming out of it and this single bond coming out of it. How would you describe the stereochemistry of that structure? What term would you use? I know y'all know this. It's trans, yeah. It's trans because these two groups right over here, they're pointed in opposite directions. They're coming out of opposite, coming out of the double bond, going in opposite directions, right? Conversely, if we had something like that, again, we're kind of describing the relative direction of those two single bonds. That's a cis arrangement, right? We've discussed that a few times. Now, with conjugated dynes, let's say you have that one right there. In this case, you'd have two double bonds, and you could describe two different stereochemical relationships. Right? You could describe the stereochemistry around this one, or the stereochemistry around this particular double bond. Trans. What about this one? Also trans. So this one has trans-trans. Yeah, we could have trans-cis as well. Mess that up. That would be an example where you had a trans in the first relationship. And then cis. You could have cis-cis. Yeah, something like this. So you see, within a conjugated dyne, and you can have more than you can have more than two double bonds in a conjugated dyne. You can have 3, 4, infinite number, right? So you see lots of different possibilities that exist for cis and or trans arrangements. Okay. Now, there is still another relationship stereochemically that we can describe, one that you haven't seen yet. And that's going to be the relationship of these double bonds around this single bond. So basically, it's the opposite of what we've previously learned. Previously, we've learned about how the single bonds are arranged around a double bond. Well, we can also describe how these double bonds are arranged from that single bond. Isn't that fun? Yeah. And you still use the term cis-trans to describe these. The only caveat is that you use an S in front of the cis or trans. As an example, right? Let's look at the relationship here. If you had to describe how this bond and this bond are arranged around the single bond, how do you think they would be arranged? Does that look like more of a cis or a trans relationship? You're looking at how these two bonds are arranged around this one. Are they going in the same direction or opposite direction? Yeah. This one's going one way, this one's going the other, around this. So that resembles a trans relationship. Since we're describing double bonds around a single bond, we call it S-trans. So there's a lot of stuff to describe here, right? Around this double bond, we have a cis arrangement. Around this double bond over here, we also have a cis arrangement. But around this single bond, we have an S-trans relationship. It's very head trippy. Let me find a couple of other good examples here. This is one of those things that when I first learned about it, I remember just being totally confused. Then it makes sense after a while. But you definitely have to get a good sort of handle on the difference between the regular cis-trans and then the S-cis-S-trans. Sorry, I'm looking at my online book trying to find things. I went a little out of order. There we go. Okay. How about this one? Looking molecule. Let's describe all the stereochemistry that's going on. Right. First of all, let's describe the stereochemistry around this double bond. What is it? Is that a cis or trans relationship?
Cis.
Around this double bond?
Oh, that's trans.
Yeah, this one is going to be trans because, again, you're looking at the relative positions of the single bonds coming out of the double bonds. You see this single bond, they're pointed in opposite directions. So that one's going to be trans. What about this one? What's the arrangement around this double bond?
Cis.
Cis, yeah. This single bond, pointed in the same direction. All right, now, what about the relationship of these double bonds around this single bond? Would that be S-cis or S-trans? S-cis. Why? Because if you look around this single bond, these two double bonds are pointed off in the same direction. Okay. that make sense? Are there any questions so far? We're gonna do some more of this. Just want to make sure you're good at this point. Okay. I'm going to give you a couple of problems here. I'm going to let you try to draw them. So what I'm going to do is I'm going to give you a name. Oh, keep forgetting I'm zooming, so I probably shouldn't pick up the laptop and start walking around with it. I was going to like walk up there, wasn't holding it so I could write the structure. Then, oh, I forgot, I have zoomers. All right, so okay, let me see if I can remember. So let's see. Let's draw 3, 5. Nonadiene. Ooh, that's not something you see very often. What's nonadiene? How many carbons? 9, yep. We're going to draw it in the S-cis. And we're using the EZ notation here. Within this context, the nomenclature context, E and Z is sometimes used interchangeably with cis trans. So in this case, you can think of E and Z being cis or trans and cis respectively. All right, take a second, see if you can draw that. I can never, well, I don't say never, I can rarely draw these perfectly just out of my head. A lot of times what I have to do is I have to draw one and see if it works. And then if it doesn't, I have to find what doesn't sort of twist the molecule in the right direction. So. Okay. All right. You can check your own at your desk. And what you actually have drawn might be slightly different depending on, you know, left or the right side where you started putting double bonds, whatever. But I'm just going to sort of show you my process. I usually like to start just by drawing, forgetting the actual problem for the most part, and just writing it in regular zigzag form. So I know I need to have 9 carbons. All right, I know I need to have double bonds at 3 and 5. So that's kind of the basic starting off point. And then I like to just go through and check, okay, what fits the requirements, what doesn't, and I can fix it later on, okay? So E, first thing is 3E. E corresponds to trans, all right? Do I have a trans relationship here? Yeah, this is trans, so I'm good there. 5Z corresponds to cis. Do I have a cis relationship here? No, so that's going to be off. All right, and then I need an S-cis configuration around the single bond. Do I have that? All right, so I have a couple of things I have to fix. All right, so I'm going to go back and redraw this. I know I've got this part right, so I want to leave that the same. I need to make this as cis, so I'm going to draw this next bond coming that direction instead. All right, so now I've got the S-cis relationship. And then finally, I need a cis relationship around this double bond, so I want to draw the next carbon like that. And then I should just be able to finish out the chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that is the correct stereochemical representation of that compound. Again, your process might differ. That's just kind of one way I like to go. Okay. Y'all see how we got that? Does that make sense? Okay. All right. One thing that's kind of interesting. Remember when we talked about cis and trans? And here, let me erase this and get something up here for you to look at. When we talked about cis-trans previously with alkenes, you know, we said that a particular structure, a particular alkene would either be cis or would either be trans, right? They're not going to be able to interconvert with each other. Why not? Why can't this particular molecule ever go to cis? Let me ask you this. Can you rotate around this bond? No, you can't rotate around double bonds. So this is locked into place. It's a little bit different for S-cis, S-trans though, because we have something like this. This is currently in an S-trans configuration, right? Because these two double bonds are pointed in opposite directions off the single bond. Can you rotate around this bond? Yeah, you can freely rotate around single bonds. So guess what? That same molecule at another point in time might exist in the S-cis configuration. And it does. You get constant rotation around this single bond. So it keeps going into S-cis, S-trans, S-cis, S-trans, S-cis, S-trans over and over and over again. Right? So most of the time, you have that ability to interconvert, with just a few exceptions. About that. What's the S-cis, S-trans configuration here? It's S-cis, right? Conjugated diene. These two double bonds, both coming off in the same direction. What's different about this one? You can't rotate around that single bond in between. Why not? It's locked in a ring, right? So this type of structure is sort of an exception to this rule. This one would always be in the S-cis. This one would always be in the S trans for the same reason. You can't rotate around that double bond. Or excuse me, single bond. Right? That's going to be an important skill for you guys to learn as you kind of go along, is looking at a molecule. Number one, figuring out if it's a S-cis or S-trans configuration. Number two, figuring out, can it rotate to the other one? And number three, if you can rotate, can I draw it correctly? Okay? And in a few minutes, you'll see why that is so. All right. Any questions so far? Sound good? All right. Okay, so, as we're exploring these compounds, you're going to see certain characteristics. Conjugated dienes, they have similarities, but as you can see, they have some differences, right? And I think the book summarizes several of these, just to kind of mention some of them, right? Conjugated dienes have extra stability. We've talked about this. You can draw resonance structures with conjugated extra resonance structures that give stability. You have a large amount of space for extra p orbitals to overlap each other, again helping delocalization. So I forgot to put the dienes here. How embarrassing. Right, so they have extra stability, right? You can make an interesting observation about bond length. And I think it's easiest to illustrate this just with a structure. That particular carbon-carbon single bond is unusually short. It's not as long as a typical carbon-carbon single bond. Any ideas why? Why would that particular carbon-carbon single bond be any shorter than, another one? What's the pattern you guys learned as far as bond lengths? Carbon-carbon single bonds, carbon-carbon double bonds, carbon-carbon triple bonds. Which one's the shortest? What's that? Triple bonds are the shortest. Single bonds are the longest, right? As you add additional pi bonds, it gets shorter, right? Well, think about this. One thing that we saw quite a bit with these structures is resonance, right? I could draw a resonance structure for this. If this pair of electrons hopped over there, push this pair of electrons over here, it could give us a resonance structure. Do these two carbons have a single bond anymore? No. They have a double bond in this resonance structure. And remember, resonance structures, none of them are actually entirely accurate. It sort of shows different representations of what can exist at any point in time. The true structure is the hybrid, which sort of lies somewhere in between, right? So if we're looking at this, that's the real structure, right? So it's almost like this has sort of a halfway double bond. And that's actually the terminology we can use, pretty close to it. This has what we call partial double bond character. Even though we usually represent it as a single bond, you can kind of think of it like this. It's got to be ready at a moment's notice to become a double bond, right? So it's got some characteristics of a double bond, some characteristics of a single bond. So that's why this one is unusually short is because it's actually got partial double bond character. We're going to see that a lot going forward, not just in this chapter, but for a lot of the stuff that we're going to be doing in upcoming chapters. We're going to see there's going to be the opportunity for resonance, and we're going to see this partial double bond character really play an important part in determination of stability and reactivity of certain molecules. Okay. Alrighty. I want to erase some of this. All right. Number 3, more conjugation. The more conjugation that you see in a particular molecule, the higher the wavelength of light absorbed. Right. Organic molecule, even inorganic molecules, everything absorbs light, right? Any type of molecule, any type of structure is going to consistently absorb something along the electromagnetic spectrum. Sometimes you can see it, right? If you see something that's, got a red color, for example, right? If you see something that's got a red color, that means it's transmitting the color red. And that means in turn, it's absorbing the wavelength corresponding to blue within the visible spectrum, right? Y'all talked about the visible spectrum in other classes. We talked about it in IR spectroscopy a little bit, right? What do most organic compounds look like? Liquids. What do most organic liquids look like? What's that? Clear. They're boring looking, right? You ever wonder why? I bet you haven't. But maybe you have, who knows, right? There's a reason for that. Most organic compounds, just like anything else, they absorb light. But they absorb light within the ultraviolet region. They absorb light within the ultraviolet region, and they transmit light in another part of the ultraviolet region. Can we see UV light? No. So that's why we can't see organic colors with organic compounds most of the time. Their particular structures don't absorb or transmit in a range that we can see. However, that can change, right? Ultraviolet light is shorter, has a shorter wavelength than visible light. If you add enough conjugation to the system, you add a little bit of conjugation, it'll still absorb UV light, but maybe in a longer range. You add some more conjugation, still longer range. If you add enough conjugation to the system, eventually you can move the absorption transmittance of a molecule even into the colored range. Right? Have you guys ever heard of a molecule called lycopene before? Seriously? You never heard of lycopene? They talk about it in commercials and stuff, like one of those antioxidant, No, I saw one for Josh. Was that you nodding? Have you heard of it? Oh, I could have sworn I saw your head nodding. Maybe I said your name and then you're like, oh crap. Yeah, I'm gonna lie. All right, let me show you the structure of lycopene. So let me open up this projector. I'm showing you here because honestly, I don't want to draw it because I'm lazy and because it's kind of large as well. Let's see. Let me share my screen with the Zoomers first. Let's see. There's so much to consider whenever you are doing Zoom and projecting at the same time. All right, so let's see. First, let me share screen with the Zoomers. There we go. And then here. Okay. Now, you can probably see it. I'll lower the lights. All right. That is the structure of lycopene. It's a big old molecule, isn't it? What can you tell me about the conjugation here? Do we have a conjugated system? Heck yeah, we do. We got a lot of it, in fact, right? You see a ton of alternating double single bonds right there. And what this does, this allows us to move into the visible range of light as far as absorption and transmittance. Can you name anything that has lycopene? Probably not, since you haven't heard of it. That would be really impressive if you could without hearing of it. What's that? Who said that? I heard it. Yeah, tomatoes. Very good. That's probably the first thing I would name, tomatoes. So what color do you think lycopene is if it's in tomatoes? It's red. You can even see a picture of watermelon down there. Yep, there it is. Also has lycopene. Lycopene has enough conjugation that it absorbs within the blue region of the visible spectrum and therefore transmits light in the red region of the visible spectrum. So we can see it. Pretty cool. How about beta carotene? Y'all ever heard of beta carotene before? Ah, I see some nods. Beta carotene is apparently more popular than lycopene. Where do you find beta carotene? Anybody know? What do they say on the commercials? And they're talking about all, antioxidants and crap. Let me show you the structure of beta carotene. Pretty similar, right? Very large conjugated system. By tweaking the number of carbons in your conjugated system, again, you can tweak exactly where it transmits and absorbs. Beta carotene is found in probably the most prominent thing that I can think of is carrots. Hey, beta carotene, carrot, huh? I don't think that's actually, I think that's just a coincidence, but still, yeah, makes sense. It's found in pumpkins, a lot of squashes. Different forms of beta carotene they can transmit sort of yellowish to orange light. So, and it's all because of this conjugation. Okay. So pretty interesting. Let me stop the projection here. And let me stop the screen share. Yeah, and that's basically why the chemical reason why you can see a lot of the colors that you see. In fact, really, there's probably two chemical reasons you can see colors, or at least 95% of most colors. One of them is due to conjugated compounds like this. The other one is due to the presence of metal ions. Y'all remember doing the flame test like in Gen Chem, where you put some, yeah, so those produce colors a lot too. But yeah, those are really the major reasons that you see a lot of different colors. And it forms the basis for a new type of spectroscopy. Yes, right? I'm hoping we'll have time to talk about it this semester called UV vis spectroscopy. We'll talk about it a little bit in this chapter. We'll see if we can get to it in lab or not. All right, and then the fourth thing on that little list of features I was making introduces special types of reactivities or reactions, right? They can do things that Other things can. We've seen one example of this already, right? We saw this with the 1,2 and 1,4 addition. However, we're about to delve into a very specialized type of reaction that's a little bit more in depth. It's used a lot in a lot of different commercial applications. And that is called the Diels-Alder reaction. You know who studied Diels-Alder reactions? Diels and Alder. All right, they did. So what is a Diels-Alder reaction? Right? Basically, it's a reaction between a diene, specifically a conjugated diene. I need to get that specific. Conjugated diene plus something called a dienophile. And it's a thermal reaction. The only additional component you need to add is heat. And every time you do a Diels-Alder reaction, you form a new 6-membered ring. Anytime you do Diels-Alder reaction, always form a new 6-membered ring. Very specific. Okay. It's also pretty persnickety. You got to have just the right accommodations, just the right conditions for this to occur. Right? So there's features. First of all, the conjugated diene. Conjugated diene must be in the S-cis configuration. It doesn't work if it's S-trans. So for that reason, you can actually take a look at the type of diene that you're using, and you can make predictions about reaction rate. Take a look at those. We have 3 potential dienes, conjugated dienes we could put in a Diels-Alder reaction. They wouldn't all contribute the same reactivity. Which one would react fastest, do you think? Number 1, 2, or 3? I see a thumb going this way. Far right. Why do you say the far right? Remember, yeah, look at the S-cis S-trans. Conjugated diene must be in the S-cis conformation to react. Well, this one's always S-cis. So that means this one's always ready to go. So that one would react fastest. What would be least reactive? One in the middle, right. In fact, it's non-reactive. We can't even say it would go slowly because it just wouldn't react at all, because it's always stuck in S-trans. And this one would sort of be in the middle. Now this one, in its current drawn state, would not be able to react because this is an S-trans. But remember, we can get rotation around that single bond, right? So once it rotates into that correct configuration, think about it. Let's see. Let's trans. It would have to rotate into this configuration before it would actually be able to react. that make sense? Any questions? All right. The dienophile. First of all, what is the dienophile? What the heck does that mean? In a nutshell, it just means you have an alkene group. It doesn't have to be just purely an alkene. You can have other stuff in there, but it has to have an alkene group. So basically a singular carbon-carbon double bond. Right. The simplest dienophile would be, just Fe. All right, just like with dienes, not all dienophiles are created equal. There are some that react faster. You get increased reactivity with the presence of electron withdrawing groups. It'll still work without them, but it goes faster with them. Electron withdrawing groups. So for example, we could have, something like that. That's just a regular old ethene. Or we could compare it to something that has like an aldehyde group hanging off of it. All right. This is electron withdrawing for a couple of different reasons. Right? We can look at the induction and the resonance. And see how much you guys remember from chapter 2. Right? Inductively, is an aldehyde group withdrawing, electron withdrawing, or electron donating? What does induction involve? Well, chapter 2. Nobody told me we'd be doing chapter 2. Y'all remember the inductive effect from acidity? What did we look at in the inductive effect?
Was it anything like carbon?
What's that?
Anything that was like attached to the carbon?
Okay. What specifically? An oxygen would be a good example, right? Remember when we talked about the inductive effect, we looked at the effects of having electronegative atoms bonded somewhere in the molecule, right? We said that like if you had, I don't know, a negative oxygen, if you had like maybe a couple of chlorines or something out here, it would sort of pull that electron density a little bit that way and stabilize. Does that sound familiar? Okay. Same type of thing here, right? We know that electron withdrawing groups stabilize, or not stabilize, but make this more reactive. That means, is this group withdrawing electron density away from Q, right? Do you see anything electronegative in this group that could do that? Yeah, you got an oxygen. So it's pulling electron density that way. So inductively, yeah, that's definitely electron withdrawing. You'll see it's also electron withdrawing due to resonance. You can draw a resonance structure for this, in which this pair of electrons moves over here, and a pair of electrons hops up to that oxygen. That. All I did was hop these electrons over, pi electrons over, hop the pair of pi electrons up to oxygen. And you can see that overall, when we draw the resonance structure, this group has sort of withdrawn or taken away electron density from these carbons. Does that make sense? So that's why we can say that, yes, this aldehyde group is very much an electron withdrawing species. Get ready, you're going to see a whole lot of that in chapters 17 and 18. All right. So, which one of these would react faster? One with or without the aldehyde? With the aldehyde, yeah. That one would definitely go faster. Right? So you can definitely have a lot of control in how fast a particular Diels-Alder reaction will go based off of the diene and based off of the dienophile that you use. All right. We are almost out of time. That's a pretty good stopping point. The next part's going to be show you how the actual mechanism of this works and all, and so I think we'll save that for Wednesday. Right. Quiz on Wednesday, this chapter up through this class. Are you, Alex and Scott, are you back on your normal schedules today? Or this week? Just check. I am almost done with your exams, just to let you know. I just have like a few more, like 3 or 4 more to grade, I think. So you should be getting that.
What will be on the
everything in this chapter up to this point. So that'd be like recognizing conjugated and non-conjugated species, 1,2, 1,4 addition, S-cis, S-trans, some of the 4 basic features of conjugated dienes. All right. No, free radical. I'm not putting free radical stuff on this. Have a good one. Katie? It's Katie. Katie, you back there? I saw that you sent me an email about your flies. I haven't had a chance to look up there yet. I haven't. Okay. Yeah, I got your email last night. I haven't noticed any, but I haven't really been looking for them either, so I don't know. Lisa, were you about to ask me something?
Yeah.